last little concept. The concept of energy is applied to the universal law of gravitation. When the force of gravity is simply mg, where g is 9.8, the potential energy, we integrated the force over the distance and came up with the potential energy equation of mgy. That works just fine as long as g is constant for your whole problem. So anywhere on the Earth, near the Earth, this works perfectly fine. But if we get to distances far from the Earth, say we're shooting a rocket into the air. If we launch a rocket, now this isn't a personal hobby rocket, so big time old rocket. If it gets launched, say at 10 kilometers per second, moving really, really fast, it's going to go really, really far. It's going to go beyond the boundaries where g is 9.8. So that won't work anymore. The mgy will not work in terms of energy. Energy can still be used We're going to make another not so good assumption. We're going to ignore air resistance at the moment.
It's going so slow, you know.
Exactly. Now we know when we deal with distances far from the Earth on an astronomical scale, the force of gravity, the actual equation we needed to use was the big G, the universal law of gravitation, the 6.67 times 10 to the negative 11, times the two masses involved in the attraction over r squared, where r was the distance from center to center. Turns out, when we integrate this force with respect to distance, integral of 1 over r squared is what? 1 over r squared is the same thing as r to the negative 2. So r to the negative 1 over negative 1. The result, we get a different potential energy equation. But we get it the same way, we integrate it. 1 over r squared integral negative 1 over r. So the equation for potential energy, when we're dealing with far distances from the Earth, is negative g m1 m2 over r. It's not r squared anymore. We integrated. So it's now just over r. The negative sign is part of the equation. That means we're going to get negative values for our potential energy regardless of where we're at, just because there's a negative sign in the function, in the equation itself. So, gravitational potential energy has a different form if we deal far distances from the Earth. Please keep in mind, when you solve any problem at all, you can use one or the other. You cannot intermix those two potential energy equations in one given problem. You can use either mgy or you use the negative gmm over r. You choose. Now, to choose, if your problem is on the Earth, if your object's going to stay near the Earth, you just use mgy. That's perfectly fine. If your problem you think is going to go far from the Earth, for example, launching something that fast, I would expect it to go pretty high, then we would use this equation for the whole problem. Okay. This equation, still perfectly valid, which, remember, is the same thing as this equation, whichever form you like to use it in. It has not changed our overall conservation of energy equation. The only thing that is changing is the potential energy equation itself. Please, also one other little note. If we're using this equation for our potential energy, you cannot say potential energy is 0 wherever you want it to be. The only place this is 0, what type of R value do you have to get U to be 0?
Infinity.
If R is 0, you get infinite.
Make it infinite.
So R needs to be very, very large, infinitely large, to get 0. So the only place the potential energy now is 0 is infinitely far away. So, for example, if we launch a rocket with a speed of 10 kilometers per second, how high is it going to go? Well, we have to have potential energy initially. R is still the distance from center to center, so it's the distance from the center of the Earth to the center of the rocket, which is going to be the radius of the Earth. Kinetic energy, so let's put these in. Instead of M1 and M2, what are the two objects involved? Earth and the rocket. The kinetic energy of the rocket, so 1/2 mass of the rocket times its initial speed squared. We know its initial speed. We're ignoring air resistance, so we don't need to worry about this work term. If we wanted to include air resistance, we would need to know an average value of the force as it was applied through the atmosphere. So the initial potential energy plus the initial kinetic energy, finally there's still going to be potential energy as well. We're going to be at a new final location. Kinetic energy, finally, what will that be? 0. When it reaches its maximum height, at that instant, it will not be moving. The gravity is going to pull it back down and it will come back towards the Earth. So the main difference is that you will have potential energy initially and finally, your equation. Turns out there's a mass of the rocket in every term. We know big G, that's a constant. We know the mass of the Earth, or at least we can look it up. It's in our book and on the test notes. We know the radius of the Earth. We were told how fast it was going. So our finals are only a known. To get our final, though, we need to cross multiply. So our final comes up to this side. All this stuff comes down to the other side. So G is 6.67 times 10 to the negative 11. Mass of the Earth, 5.98 times 10 to the 24, I believe. If someone wouldn't mind looking up the radius, it's like 6.3 something. I think it's in the back cover of your book.
6.37 times 10 to the 6th.
Thank you. So G, mass of the Earth, radius of the Earth. Initial speed needs to be in meters per second, so 10,000 meters per second. Plug and chug all of that in. This is when I wish my calculator would work. those of you plugging it into, let me know. I get 3.16 times 10 to the 7th meters. Where will this be measured from, by the way? Center of the Earth out to where the rocket is now. So does that quite answer the question? No. To answer how high will it go, we need to subtract from this the radius of the Earth. So the height that would be how high it goes, assuming I plug those numbers in correctly. Questions? I need to double check my calculations. Once I subtract off the radius of the Earth, that's what I got. Okay. So the nice thing about chapter 13 is we're not reinventing the whole conservation of energy. We just have one little equation we have to substitute in. In place of mgy, we need to use the negative gmm over r. Your homework problem, you have a homework problem, for example, where you have an asteroid headed towards Earth, and it tells you how fast the asteroid is moving and how far away it is. And it asks you, if it were to collide with Earth, how fast would it be moving upon collision? Since we're talking astronomical scales, the asteroid is really, really far from the Earth. You're told initially how far away it is. You know the mass of the asteroid. You know the initial speed of the asteroid. And you're asked for how fast, basically what's its impact speed? How fast will it be traveling when it collides with the Earth? So it's the same thing. You look at the potential energy between the Earth and the asteroid. You have some initial position where it's at, so you have initial potential energy because of where it's at. You have kinetic energy that the asteroid has because it's moving. We're not worrying about the speed of the Earth. The speed of the Earth isn't changing, well, not significantly from when the asteroid is this far away to right before it hits the Earth. So the kinetic energy of the Earth isn't changing. So that's why we don't need to worry about the kinetic energy of the Earth. You are told to ignore drag. So all the potential and kinetic energy you start with has to equal the potential energy. What's the final R? Radius of the Earth, exactly right. Plus whatever kinetic energy the asteroid has, finally. You're looking for that V final. Turns out you don't actually need the mass of the asteroid. The only way you would need the mass of the asteroid is if you were told to take into consideration air resistance. So if you were to include drag, then you would need the mass of the asteroid. You're just solving for the final V. You know the radius of the Earth, the mass of the Earth. You're told the initial speed and the initial position, how far away it is from the center of the Earth. So you can find the final speed. And then it throws things up and it gives you part B and it says, what if it was to miss the Earth by a certain distance? How fast would it be going as it passed by the Earth? What would that change? So if instead of being on a head-on collision where it's going to crash into the Earth, Earth's over here, and it's going to pass by. It tells you how far it passes by.
The rate
Trigger
would be Earth's radius plus.
Break it into parts.
You should have to worry about the radius.
All you have to do is add that extra little distance and miss by. That's it. Still has the same initial potential and kinetic energy. The only difference is how far it ends up being at your final position. Energy's really cool that way. You just need to know where it is and how fast it's going, and you're good to go. One last little equation that is derived from this is sometimes you'll hear astronomers talk about escape speed. For example, when we launched, not too long ago, they launched a probe to head out to Pluto. They're going to go circle Pluto and take some good pictures and stuff. In order to get it out to the outer regions of the solar system, we need to escape the effects of Earth's gravity. Because Earth, if we don't shoot it off fast enough, Earth pulls it back in, and it becomes just a regular projectile. It'll come back and crash into the Earth. There's a certain speed at which we need to escape the effects of gravity.
Is it a distance or is it a speed that you have to have?
It's a speed.
It's not a distance. So once you get
Well, you have to have a certain speed at a certain position. So depending upon where you are, there's a certain speed you have to have. So this equation for escape speed assumes that you have that speed immediately. So your rocket gets you moving that fast. There's certainly a lot more to take into consideration. Escape speed is trying to get you infinitely far away from the Earth. But escape speed is the absolute minimum speed you could be going to make this happen. So that means you're going to be left with no kinetic energy. The escape speed is the absolute minimum you can get a rocket or whatever you have, shuttle, going in order to get it away from the effects of the Earth. Same equation. Gravitational potential energy, mass of the spaceship, whatever it happens to be. It's starting on the Earth, so the initial R needs to be the radius of the Earth, plus the kinetic energy that it has. This will be the escape speed specifically. If R is infinity, what happens to our potential energy equation? It goes to 0. Since escape speed means the minimum amount of energy to get you out there, it's not leaving you with any energy left to do anything, so it's not particularly helpful. This is just the absolute minimum speed you'd have to travel. Mass of the spacecraft will cancel. So mass of the shuttle, the mass of the rocket, whatever it is that's going. Taking that to the other side, we'll multiply by 2 and then take the square root. So that's the absolute minimum speed an object must be traveling in order to escape the effects of the Earth.
If this has a final velocity of 0, it's not really going to do anything once it leaves Earth.
Certainly, it's just going to be stuck out there.
So it's like
So if you're really going to be launching a probe and you want it to keep moving, you got to launch it faster.
You're just basically launching a piece of trash out there.
Exactly.
That's something American would like.
True. True.
They're like, well, we screwed up, so it's just sitting there, and then we go and give it a push. And then they have a couple $1 million. You go up there, send the astronauts up, they put a booster on to push it out now.
So it's just over 11 kilometers per second. Very fast. Now granted, if you've ever watched a rocket launch, the rocket is not traveling really fast right as it leaves the launch pad. The rocket boosters, the rockets keep firing for quite a while. They continue accelerating the rocket faster and faster and faster. This type of thing, yes. Okay. So when astronomers are planning on putting something into space, for example, the probe they're sending out to circle Pluto, they need to take into consideration how fast they need it to get going. Now they do piggyback on Jupiter, for example. They'll let it go by Jupiter and let Jupiter speed it up on its way, so it gets some energy from there. They also have to take into consideration the escape speed from the sun. The sun is trying to pull everything back into it as well. So it's certainly more complicated than this when you come to real practice. For now, we'll just look at escape speed, say, from the Earth, or just look at conservation of energy.